Okay, so today we are going to explore one of the fundamental building blocks of modern electronics, which is the PN junction diode. This seemingly simple structure is at the heart of the diodes, transistors, solar cells, and countless other semiconductor devices that make our modern electronic world possible. So let's get started by looking at what's shown on the first slide. Here we have the basic uh, structure of a p-n junction, a boundary between p-type and n-type semiconductor materials. On the left-hand side, we see the p-type region, which has an abundance of holes as majority carriers. And on the right-hand side, we have the n-type region with the electrons as majority carriers. The diagram also illustrates donor atoms coming into the n-type material. So here, donors, yeah. And remember that donors are atoms that provide extra electrons to the semiconductor lattice. Typically, atoms like phosphorus or arsenic in silicon, which have one more valence electron than silicon needs for its covalent bonds. So as shown in below, we see the current versus voltage characteristic curve of a n junction. This asymmetric behavior is what makes diodes so useful. When we apply a forward bias, positive voltage to the P side and negative bias to the N side, the current across the PN junction diode flows relatively easily after overcoming the built-in potential. However, when we apply a reverse bias, almost no current, not really zero, but almost no current flows except for a very small leakage current. So finally, at the bottom right-hand side, we see a standard diode symbol. The arrow in the symbol, this guy, yeah, the arrow in the symbol points in the direction that conventional current flows when the diode is forward biased. Think of it as pointing from P to N, the same direction positive charges would move. This asymmetric conducting behavior is what makes diodes essential for converting AC to DC, protecting circuits from voltage spikes, and many other applications we will explore as we go deeper into the physics of PN junctions. Okay, let's move on to the next one. The second slide, the key focus herein is on understanding doping profile in PN junction diode. So doping profile describes how the concentration dopants varies across the semiconductor. On the left-hand side of the diagram, we see two curves representing doping concentration here, N sub A and N sub D. The curve labeled N sub A shows how the concentration of acceptor atoms, like a boron in silicon, diffuses into the semiconductor from the surface herein. It is noteworthy that how it's highest at the left edge and gradually decreases as we move toward the right-hand side. This is a physical profile we would like to see after diffusion doping processes. Below it, we see N sub D, which represents the initial uniform donor concentration in the substrate or wafer. At the bottom of the left-hand side, we see the physical structure showing the metallurgical junction. This is the point where N sub A equals N sub D, or equivalently where N sub D minus N sub A equals 0. This is the physical boundary between p-type and n-type regions. On the right-hand side, it shows the net doping concentration, N sub D minus N sub A, across the junction. Above the x-axis, the material is effectively n-type, and below it is effectively p-type. Think of it like a political map during an election. If we consider Democratic voters as acceptors and sub A, And Republican voters as donors, then the N sub D minus N sub A graphs shows which party has the majority in each region. The methodological junction is like the exact boundary where the majority flips from one party to the other party. This terminology is very crucial because the shape of this doping profile affects many electrical characteristics of the junction, including its capacitance, junction capacitance, diffusion capacitance, breakdown voltage, and switching speed, such transient characteristic, I mean. All right. Okay, uh, now that we understand the actual doping profile in real devices, let's take a look at how we typically idealize these profiles for analysis. In this slide, we see two common idealizations that make our mathematical treatment more tractable. On the left side, we see a comparison between an actual profile and what we call a step junction idealization. In this approximation, we assume the transition from p-type to n-type happens abruptly at a single point here. This is similar to how we might approximate a gentle hill as a cliff in a simplified map. While real diffused junctions have a gradual transition, the step junction model gives us a good first approximation that greatly simplifies our calculations. On the right-hand side, we see another idealization, the linearly graded junction. Here, instead of an abrupt step, as we have just seen on the left-hand side, we approximate the transition region with a straight line here. This is more accurate for certain type of junctions, particularly those made by epitaxial growth or ion implantation with specific process conditions. These idealizations are analogous to how we might simplify other physical systems. For instance, when we study the motion of a pendulum, we often start with the idealization of a simple harmonic oscillator, ignoring air resistance and other complications. Similarly, these junction idealizations give us mathematical models that capture the essential physics while remaining solvable. Throughout this lecture, today's lecture, we will primarily use the step junction model on the left-hand side because it provides the clearest illustration of the key concepts that we are going to learn. However, keep in mind that in advanced device design and analysis, more sophisticated models might be necessary. Okay, so here we are going to look at the outline. So in this lecture, we will be focusing specifically on PN junction electrostatics. This is the foundation we need before moving on to the dynamic behavior and applications of these PN junction diodes. Understanding the electrostatics, for example, the electric fields, electric potentials, and charge distributions across a PN junction at equilibrium and under bias conditions. Yeah, understanding those electrostatics is like understanding the anatomy of an animal before studying its behavior. We need to know the structure before we can fully appreciate the function. So in particular, we will explore number one, the built-in potential that exists across the junction even without any external voltage. Number two, the depletion region, what it is, why it forms, and how it responds to applied voltage. Number three, the electric field and potential distributions within the junction. Then lastly but not least, how to mathematically derive these quantities from basic semiconductor physics. So this whole understanding will serve as the foundation for our future discussions on PN junction devices and their applications in electronic circuits. Okay, now let's move on to the next slide. Okay, here. In this slide, we're going to look at the qualitative electrostatics. Now let's develop a qualitative understanding of the electrostatics within a PN junction before diving into the mathematical details. As shown in this slide, there are four interconnected aspects we need to understand: the band diagram, electrostatic potential, electric field, and charge density. These are all different ways of viewing the same physical reality. Starting at the bottom with the charge density, denoted as rho, when we bring p-type and n-type semiconductors together, we get a region where positive charge exists on the n side from ionized donor atoms that have lost their electrons, and negative charge exists on the p side from ionized acceptor atoms that have gained electrons. This separation of charge is crucial, key to understanding everything else. Think of this like a crowd at a concert where fans of two different bands are separated, positive charges on the one side, negative on the other, with a relatively empty space in between. Moving up to the electric field here, denoted as electric field E. This charge separation creates an electric field pointing from positive charge towards negative charge, from the n side to the p side, actually. The field is the strongest at the junction here at x of 0 and diminishes as we move away in either direction. Next, the electrostatic potential denoted as V. The electric field creates a potential difference across the junction, with the N side at a higher potential than the P side. This potential variation is shown in the graph here, with the total built-in potential labeled as V sub I. Finally, at the top, we have the band diagram. This band diagram shows how the energy bands bend in response to the potential. The conduction band edge is of C, valence band edge is of V, and intrinsic Fermi energy level is of I, all band downward, going from the N side to the P side. The Fermi energy level, denoted as E sub F, remains constant throughout the device at equilibrium. So imagine these bands as layers of a landscape that get bent downward like a water slide going from N to P side. This band bending creates energy barriers that affect how carriers move across the junction, which ultimately determines the electrical characteristics of diodes and other devices. All these aspects, I said, charge, field, potential, and energy bands, are different facets of the same underlying physics, connected through max application, Poisson's or and semiconductor physics principles. So now that we have a quantitative understanding from the previous slide, let's build up a systematic approach, our game plan for quantitatively analyzing PN junctions. We will work from fundamental principles to derive expressions for the charge density, rho of x, electric field, E of x, and potential V of x. First, we will find the built-in potential V sub Vi. This is the potential difference that naturally exists across the junction at thermal equilibrium without any external bias. It arises from the diffusion of carriers when the two semiconductor types are brought together. Next, we will use what's called the depletion approximation to determine the charge density rho of X. This approximation assumes that the junction regions is completely depleted of mobile carriers, leaving only the fixed charges from ionized dopant atoms. Think of it like a demilitarized zone, DMZ, where all the civilian populations, for example, mobile carriers, has been evacuated out, leaving only fixed military installations, which would become the ionized dopants. And with the raw wax in your hand, we will integrate to find the electric field E of X, applying the boundary conditions that the field must go to zero at the edges of the depletion region, at x of minus xp and x of xn. This makes physical sense because beyond the depletion region, the semiconductor becomes electrically neutral again. Then we will integrate the electric field E of X to obtain the potential V of X using boundary conditions that set V of X of minus XP 0 as a reference point. And another boundary condition is V of X of Xn equals V sub VI, total built-in potential across the junction. Then we will integrate electric field E of X to obtain the potential V of X using, finally, we will apply the condition that the electric field must be continuous at X of 0, the junction junction interface, metallurgical junction. And this gives us the relationship n sub A times X sub P equals n sub D times X sub N, which will allow us to solve for the depletion with X sub P and X sub N. This systematic approach, as I have just described, is like solving a mystery by following a chain of evidence. Each step gives us new information that builds on previous findings, ultimately giving us a complete picture of the electrostatic conditions in the PN junction. Okay. So now let's take a look at the built-in potential vis-a-vis as the first one in PN junction diodes electrostatics. Let's now derive the built-in potential vis-a-vis I, which is one of the most important parameters characterizing a PN junction diode. The built-in potential vis-a-vis I is the voltage that naturally develops across the junction when P and N regions are brought together, even without any external bias. As shown in this equation at the top of the slide, here. As shown in the equation at the top of the slide, the built-in potential can be expressed as the difference in electrostatic potential between P side and N side. Here, Q sub Bi equals phi as P side minus phi sub S N side, or EI minus EF on P side plus EF minus EI on N side. Here, E sub I is the intrinsic Fermi energy level, and E sub F is the Fermi level. The terms E sub I minus EF and EF minus EI represents the energy differences between these levels on the P side and N side respectively. So looking at the Venn diagram, we can see this graphically. The built-in potential Q sub VBI is represented by the total band bending here, total band bending from one side to the other. For non-degeneratively doped material, which is the typical case for most semiconductor devices, we can express these energy differences in terms of carrier concentrations, as denoted on the bottom side. Well, definitely here, N sub A indicates the acceptor concentration on the P side, N sub D indicates the donor concentration on the N side, and N sub I is the intrinsic carrier concentration of the semiconductor. For instance, N sub I for silicon is 10 to the 10 per cubic centimeters. This is analogous to the potential difference that develops when two water tanks with different water levels are connected by a pipe. The built-in potential is like a pressure difference that would derive water flow if not for a valve, which in our case is the energy barrier of the junction. The built-in voltage typically ranges from zero point 0.7 to zero point 0.8 volts for silicon PN junctions at room temperature, depending on the doping concentration. So you may calculate it. This built-in potential creates an energy barrier that carriers must overcome to cross the junction, which is the fundamental to how diodes function. So now let's take a look at the built-in potential for one-sided PN junction. So I mean the uh, one of the one of the P side, either P side or the N side are degeneratedly doped, then we can call this PN junction diodes as one-sided. So having established the general expression for the built-in potential from the previous slide, let's examine special case known as the one-sided junctions. These are PN junctions where one side is much more heavily doped than the other side. So this slide shows the same basic equation for the built-in potential Q sub VBI is equal to E sub I minus EF. Oh, there we go. Yeah. The same equation for built-in potential, but now we are looking at two specific cases, P plus N junctions or N plus P junctions. So P plus N junction indicates here the P side is much more heavily doped than the N side. So indicated by the plus superscript here. So this means that N sub A is much higher than N sub D. What about the N plus P junction? The opposite case, where the N side is much more heavily doped than the P side. So N sub D is much higher than N sub A. So taking into account these two inequality, you may quantitatively estimate the built-in potential for each one-sided PN junction. So these one-sided junctions are extremely common in practical devices, actually. For example, many diodes are fabricated as N plus P junction because this configuration, N plus P junctions, offers advantages in terms of switching speed and breakdown characteristics. The key insight for one-sided junctions is that depletion region extends much further into the lightly doped side. This is similar to how when a small country borders a large one, any neutral zone between them would extend much further into the larger country to balance the resources or power from both sides. For P plus N junction, since N sub A is much higher than N sub D, we have the X of P is much narrower than the X of N. The depletion width on the P side is much smaller than the on the N side. So similarly, for an N plus P junction, X of N is much narrower than the X of P. So this asymmetry has important implications for device characteristics, actually. For example, in a one-sided PN junction, most of the built-in potential drops across the lightly doped region, making the electric field distribution and capacitance behavior different from a symmetrically doped junction. So understanding one-sided junctions is very crucial because they are the building blocks of many practical semiconductor devices in IC chip, from regular diodes to specialized structures like a PIN diodes, Schottky diodes, and pulse of transistors, such as source and drain regions or MOSFET. So now let's take a look at the depletion approximation. We will introduce a powerful simplification called the depletion approximation, which helps us analyze the electrostatics of p-n junctions with reasonable accuracy while keeping the mathematics manageable. The depletion approximation makes two key assumptions. Number one, inside the depletion region, from minus xp to x of n, there are essentially no mobile carriers, only fixed charges from ionized dopants. Number two key assumption is outside the depletion region, the semiconductor is neutral and has no net charge. So this creates a charge density profile as shown in the figure. On the p side, from here to there, the charge density rho is simply equal to the minus q times n sub a. Negative charge from ionized acceptors. On the n side, from 0 to x of n, the charge density, this value, is equal to plus q times n sub d, positive charge from ionized donors. So think of the depletion region like a battlefield that have been evacuated of civilians, which is corresponding to the mobile carriers. So leaving only the fixed installations, ionized dopants. So this creates a clear separation of charge that we can analyze more easily. So with this charge distribution, as shown in the slide, we can find the electric field by integrating the Gauss's law. D sub E dE dx is equal to charge density divided by the E sub silicon, the electric constant of silicon. On the P side, this gives us electric fields. E sub A is equal to this, where we have determined the integration constant C1 by applying the boundary condition that E sub E electric field at XO minus XP is equal to 0. The field must vanish out at the edge of the depletion region. So similarly, on the N side, the electric field is equal to this. Again, we have used the boundary condition that electric field at x of xn is equal to 0. These equations give us the electric field throughout the junction. So it is noteworthy that the field is maximum at x of 0, which is the metallurgical junction, and decreases linearly as we move away in either direction, reaching 0 at the edges of the depletion region. The depletion approximation, while it is not super perfect, provides an excellent basis for understanding p-n junction behavior and is accurate enough for most device analysis purposes. So now let's take a look at the electric field in the depletion layer. A critical constraint in our analysis is that the electric field must be continuous at x of 0 metallurgical junction. So this physical requirement leads to an important relationship between the depletion width and doping concentrations. So from our previous slide, we have derived expressions for the electric field in both regions. On the P side, the electric field was Q times N sub A divided by epsilon S times X plus XP. And on the N side, the electric field was, I may not be super correct, but take a look at the details on the previous slide. So at X equals 0, these two electric fields should be equal to each other. So simplifying it, we can get N sub A times X sub P equals N sub D times X sub N. So this elementally simple relationship tells us that the depletion region extends further into the lightly doped side of the junction. It is like two countries establishing a demilitarized zone between them. The smaller country more heavily doped region gives us less territory than the larger country lightly doped region. So for instance, if the N side has 100 times the doping concentration of the P side, then the depletion risk on the P side will be 100 times larger than on the N side. Okay. So this principle is extremely useful in device design. By controlling the relative doping concentration on each side, we can engineer how the depletion region distributes itself, which affects properties like capacitance, breakdown voltage, and switching speed. So in particular, for the one-sided junctions we discussed earlier, P plus N or N plus P, the depletion region exists almost entirely in the lightly doped side. So this simplifies our analysis even further and is a common design approach for many practical devices. So now let's move on to the electrostatic potential in the depletion layer. So now that we have established the electric field distribution, our next step is to find out the electrostatic potential throughout the depletion region. We will do this by integrating the electric field, since electric field is equal to minus dV dx. Okay. So on the P side, we integrate our electric field expression. Integrating gives us v of x is blah, 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 with a constant d1. So where d1 is an integration constant. So following our game plan that we have studied a few slides ago, we will set 3x minus xp is equal to 0 as our Laplace potential, which gives us d1 is equal to 0. So on the P side, v of x is equal to q na 2 times epsilon x plus xp square. So similarly, on the N side, we integrate electric field and to get potential V of x, as shown in this equation. So to determine the integration constant d2, we can use the condition that V x of xn is equal to V sub vi. The full built-in potential is reached at the edge of the depletion region on the N side. So this gives us the D2 is equal to VBI. So our potential on the N side, V of X is equal to that. Okay. So think of this potential distribution like a hill, starting from the P side at X of minus XP, which is corresponding to the altitude of 0. The potential rises as we move forward the junction. First with the parabolic shape with the upward curvature on the P side. Then with a parabolic shape with a downward curvature on the N side. Finally reaching its maximum height, VBI, at X of Xn. So this potential profile creates the energy barriers that control how carriers, electrons and holes, move across the junction, which directly influences the current voltage characteristic of diode devices. All right, now let's take a look at the continuity conditions. So to wrap up and complete our PN junction diode analysis, it is necessary to apply one more critical constraint, the electrostatic. The electrostatic potential must be continuous at the metallurgical junction of X of 0. This will give us the equations we need to solve for the depletion with XP and XN. So at X of 0, the potential expression from both sides must be equal. So Q and A to epsilon S XP square is equal to VBI minus Q and D Excellent scale. So we also know from our electric field continuity conditions that n sub a times xp equals n sub d times x sub n. So these two equations allow us to solve for xp and xn in terms of the known parameters such as na and d, vbi, and epsilon s. So after some algebra, which I will leave as an exercise for you, we can derive that x of p, let me see here, x of p and x of n. And the total depletion width, W, which is the summation of xn and xp, is equal to this. So these expressions tell us how wide the depletion region is and how it distributes itself between the p and n sides based on the materials and doping concentrations. For example, in a silicon PN junction with n sub A, n sub D all 10 to the 16 per cubic centimeters, the depletion at thermal equilibrium is typically a few tenths of a micrometer, extremely small, right? But critical to device operation. So this completes our analysis of PN junction electrostatics at thermal equilibrium. In our just one side of the junctions, I'm gonna leave this material for your exercise and some example problems set from textbook and summary note. So this completes out our analysis of PN junction electrostatics at equilibrium. In our next session, next class, we will examine how these parameters change when we apply an external bias voltage, which is the key to understanding diode behavior in actual integrated circuits. Okay, so let's have some 5 to 10 minutes break. Okay, so now let's take a look at the PN junction current versus voltage characteristics. So this slide introduces the next topic in the series, PN junction IV characteristics. So having established the electrostatics of the junction at thermal equilibrium, we will now explore what happens when we apply external voltages and current flows. There is also an important note about practical semiconductor devices. In real integrated circuits, PN junction often aren't formed by directly joining p-type and n-type materials. Instead, they are created through counter-doping, the process of introducing dopants of opposite type into a region that is already doped. So when applying our equations to such junctions, we need to work with the net doping concentrations. So n sub A represents n sub A minus n sub D on the p side, the excess of acceptors over donors, and n sub D n sub D represents the ND minus NA on the N side, the excess of donors over acceptors. So this distinction becomes important in advanced device design where precise control of doping profile is critical. Now, let's take a look at the linearly graded junction. So while we have focused on the abrupt junction, where doping changes suddenly at metallurgical junction, real devices are often having doping profiles that can change gradually. A linearly graded junction is one where the net doping concentration n sub D minus n sub A changes linearly with distance. So this slide shows 4 key graphics. Number 1, doping profile, a straight line crossing the origin. Number 2, the charge density also linear, but with a discontinuity at the junction, right? And the electric field, which follows a parabolic profile, the potential V, which has a smooth curved shape. So in a linearly graded junction, the depletion region extends symmetrically on both sides of the junction, about W over 2 into each side. The electric field reaches its maximum at the metallurgical junction X of 0 and decreases to 0 at the edges of the depletion region. So this type of junction is often encountered in devices where diffusion processes naturally create gradual doping transitions, or where specific graded profiles are engineered for particular electrical characteristics. The physics and mathematics of graded junctions are more complex than abrupt junctions, but the fundamental principles remain the same. Charge neutrality must be maintained, and Poisson's relates charge density to electric field and potential. So now let's take a look at the biased PN junctions. Now we examine what happens when we apply external voltage to a PN junction, the foundation of the diode behavior in real. The diagram herein shows a PN junction with applied voltage V sub A. Importantly, this applied voltage primarily drops across the depletion region here. The rest of the P and N regions have negligible voltage drop because of their relatively high conductivity. This is analogous to a series circuit with a large resistor, the depletion region, and two small resistors, the P and N regions. Most of the voltage drops across the large resistor. For this model to be valid, a key condition must be satisfied. V sub A should be significantly smaller than the V sub Bi. This condition ensures low-level injection, meaning the injected minority carriers do not significantly alter the majority carrier concentrations. So if V sub A becomes comparable to V sub Bi, high-level injection occurs, and our simplified model breaks down. This typically happens at higher currents where the diode's behavior deviates from the ideal exponential relationship. The diagram also points out, negligible voltage drops at the ohmic context here, where metal connects to the semiconductor, and in the neutral region here and there on either side of the junction. This allows us to focus our analysis on what happens at the junction itself. Okay. So this slide illustrates, here. So this slide comprehensively illustrates how applying different biases affects the physical properties of the PN junction. The left side shows how the depletion width W changes with bias. Under reverse bias, W increases, right? And at equilibrium, W has its natural width. Under forward bias, W decreases. So similarly, the charge density rho, electric field E, and potential distribution V all changes with bias. On the right-hand side, we see the energy band diagrams for different bias conditions, VA, forward, and reverse. So at equilibrium, the Fermi level, aligns, and the bands is conduction band and valence band. Those two bands bend to create the built-in potential barrier here. And under forward bias, the barrier height here decreases, VBI minus VA, making it easier for carriers to cross. Under reverse bias, the barrier height, VBI minus plus VA, because this is a negative value. To take a magnitude of the negative value of the reverse bias, you can claim that the total potential barrier height has been increased from VBI to VBI plus VA. So under reverse bias, the barrier height increases, making it harder for carriers to cross. So forward bias reduces the depletion width and barrier height, allowing more current to flow as carriers can more easily overcome the reduced barrier. This is why diodes conduct well in the forward direction. The reverse bias increases the depletion width and barrier height, severely restricting current flow. Only a small number of thermally generated carriers have enough energy to overcome this increased barrier, resulting in minimal reverse current. So this asymmetric response to bias, conducting well in one direction but blocking in the other, is the fundamental property that makes diode useful as one-way electrical bulbs. So now let's take a look at the PN junction electrostatics when vis-a-vis is non-zero. So this slide provides a mathematical description of a PN junction under applied bias. The built-in potential vis-a-vis I remains the same as in the equilibrium case. However, the effective barrier height becomes VBI minus VA. Under forward bias, this barrier decreases. Under reverse bias, it increases. The depletion width W is now given by W XP plus XN. Notice herein that how the applied voltage VA appears alongside VBI. Yeah. As VA increases, under forward bias, the depletion width decreases. As VA becomes negative, under reverse bias, the depletion width increases. The equations for how far the depletion region extends into each side remain proportional to the relative doping. X of P is this, and X of N is described with this equation. Okay, again, the equation for how far the depletion region extends into each side remain proportional to the relative doping. Okay, so these equations tell us the side between the side with lower doping will have a greater portion of the depletion region. This makes intuitive sense. The weaker side with fewer dopants gets pushed more by the electric field. So understanding these relationships is crucial for designing diodes with specific breakdown voltages, capacitances, and switching speeds. All properties that depend on the depletion width and its response to bias. So this slide continues our discussion of bias to PN junctions, focusing on the electric field and potential distributions. So the electric field distribution E of X varies across the depletion region, reaching its maximum magnitude at the junction interface. The field is created by the fixed charges of the ionized dopants and plays a crucial role in determining junction behavior. The potential distribution V of X, V of X shows how the voltage varies across the junction. An important point highlighted is at the junction interface of X of 0, the potential is V of X, V of 0, as described as shown in here. So this tells us that the potential at the junction depends on both the built-in potential, the applied voltage, and the relative doping levels. For a one-sided junction where one doping is much higher than the other, most of the potential drops across the lightly doped side. So understanding these distributions is vital for advanced device design, particularly for power devices where electric field management is critical to prevent premature breakdown. So now let's move on to the peak electric field. So the peak electric field at a PN junction is a critical parameter, especially for power devices, where it determines the breakdown voltage actually. So the slide starts with an important relationship uh, as shown in here. This equation relates the area under the electric field curve to the potential difference across the junction. For a one-sided junction, we previously derived that W as shown in here. So by combining these equations, we can determine the peak electric field E of 0 at the junction as described here. So this reveals something important. The peak electric field increases with the square root of the doping concentration. So this is why highly doped junctions break down at lower voltages. They develop higher electric fields for the same applied voltage. So in practical terms, if we want to create a high voltage diode that can withstand the large reverse biases without breaking down, we should use relatively light doping in the region that supports the depletion region. Okay. So now, yeah, if you need some time to break, yeah, please go ahead and stop my recorded lecture and take your own time. So now let's move on to the current flow qualitative perspective. So this slide provides a qualitative understanding of current flow in PN junctions under different bias conditions. The four diagrams, number A, equilibrium, so equal and opposite carrier movements result in zero net current. And B, forward bias is higher than zero. Reduce the barrier here. So reduce the barrier allows majority carriers to cross the junction easily. And number C, reverse bias, when VA is less than zero, increase the barrier height. And here, increase the barrier height severely restricts current flow. And figure D, current versus voltage characteristic. So it shows the exponential relationships between current and voltage under forward bias. Under reverse bias, a constant leakage current is flowing. So in equilibrium, thermal generation creates a small current in each direction, but they exactly balance out, resulting in zero net current. Under forward bias, electrons from the N side and holes from the P side can more easily overcome the reduced barrier, creating substantial current flow. Under reverse bias, the heightened up barrier makes it extremely difficult for majority carriers to cross over the junction. Only a small reverse saturation current flows, mainly due to minority carriers. So the resulting IV characteristic shows this asymmetric behavior. Exponential current growth in forward bias, but nearly constant and very small current in reverse bias. So this is the fundamental behavior that makes diodes so useful in electronics. They act as a one-way valves for electric current, allowing flow in one direction while blocking it in other. All right, so now let's dive into some more details how the current flows in a PN junction diode. So from now on, we are diving into the fascinating world of a PN junction diodes and how current flows through these fundamental semiconductor devices. So let's begin with what happens when we apply a forward bias to a PN junction. When you say forward bias, we mean applying a positive voltage, VA is higher than zero, to the P side relative to the N side. What happens then is quite interesting. The potential barrier that normally exists at the junction becomes smaller. Think of this potential barrier like a hill between two valleys. In equilibrium, no applied voltage. This hill prevents most carriers from crossing between regions. When you apply forward bias, We are essentially lowering this hill, making it easier for carriers to cross. So this leads to what we call minority carrier injection. What does that mean? Well, in the p-type region, the minority carriers are electrons, and in the n region, the minority carriers are holes. So when we lower the barrier, more of these minority carriers can cross into the opposite region than they could at equilibrium. In mathematical terms, we represent this as delta n sub p higher than zero, delta p sub n higher than zero, indicating an increase in minority carrier concentrations. So once these minority carriers are injected across the junction, they diffuse into what they call the quasi-neutral regions. Think of these carriers like explorers entering new territory. As they move deeper into this territory, they eventually recombine with the majority carriers in those regions, similar to how a drop of ink eventually disperses in water. Okay. So now let's take a look at the current density equations. Let's look more closely at how we mathematically describe the current flow through a diode. The total current density J is the sum of two components, the electron current density J n of x and the hole current density J sub p of x. It's worth noting that while the total current density J remains constant throughout the diode due to the current continuity, the individual components at J sub n of x and J sub p of x can vary with position. So let's examine the equations for these current densities. So for electrons, uh, J sub n of x is a drift current component plus diffusion current component. For holes, similarly, drift current components and diffusion current components. So these equations might look intimidating, but they represent two fundamental transport mechanisms. Number one, drift current. The first term with the electric field E here represents carriers moving due to an electric field, like leaves being carried by a lever current. Number two is diffusion current. The second term with the derivative represents carriers moving due to concentration gradients, similar to how perfume molecules spread out from an area of high concentration to low concentration. So in a diode, both mechanisms contribute to the overall current flow, but as we will see, diffusion often dominates in the quasi-neutral region, not drift, but diffusion quite often dominates in the quasi-neutral regions in the PN junction diode. So now let's take a look at the assumptions for ideal diode analysis. So before we can develop a mathematical model for an ideal diode, we need to make some simplifying assumptions. So think of these as the rules of the game that allow us to solve the problem more easily while still capturing the essential physics. First, we assume we have a non-degenerately doped step junction. Okay? This means that the doping changes abruptly from p-type to n-type, like a stepping off a curb rather than walking down a gentle slope, and the doping levels aren't extremely high. Second, we assume steady state conditions. This means we are looking at the system after all transient effects have settled out, similar to analyzing water flow in a pipe after the faucet has been opened for a while. And third, we assume low-level injection conditions in the quasi-neutral region. This means the injected minority carrier's concentration is much smaller than the majority carrier concentration. Like adding a small amount of salt to a larger pot of water, it doesn't significantly change the overall concentration. Finally, we assume recombination generation is negligible in the depletion region. This is like saying the carriers travel throughout the depletion region so quickly that they don't have time to recombine or generate. So this last assumption gives us an important mathematical consequence. J's of n and J's of p are constant inside the depletion region, expressed as uh, derivative of Jn with respect to x is 0. Okay, so this significantly simplifies our analysis in the end. So now that we have just established our assumptions, let's outline the approach for analyzing the ideal diode. The very first step is to solve the minority carrier diffusion equation in the quasi-neutral regions. Our goal is to find the excess minority carrier concentrations here, delta n of p, delta n sub p, and delta p sub n as a function of location and bias that you applied. To solve these equations, we need boundary conditions definitely. On the p side, we need to know delta n sub p when x is minus xp and when x is minus infinity. On the n side is as follows. So the values at the edges of the depletion region, minus hp and xn, will be determined by the applied voltage, while at great distances from the junction, I mean the plus minus infinity, excess carriers approach zero definitely. So after finding these carrier distributions, we determine the minority carrier current densities in the quasi-neutral regions using those two equations. So notice here that in the quasi-neutral regions, we have dropped the drift terms because the electric field is negligible in the quasi-neutral region. So lastly but not least, we can evaluate J sub n at x of minus xp and J sub p at x of xn. And we will sum them up to get the total current, J as a function of applied voltage here. So this approach is somewhat like calculating the flow rate of the water in a complex pipe system by analyzing the pressure differences and pipe characteristics at key locations. All right, now let's take a look at the carrier concentration at depletion edges, minus xp and xn. So let's begin by understanding the carrier concentrations at the edges of the depletion region. First, consider the equilibrium case. On the p side at x of minus xp, we have pp naught n sub a, the majority carrier equal to acceptor concentration, full ionization assumed, and n sub p naught is equal to n sub I divided by n sub a, which is the mass obtained from the mass section law. I mean, the minority carriers can be simply determined by using the mass section law. Similarly, on the n side, at x of xn, n naught is equal to n sub the majority carrier equals the donor concentration, full ionization assumed, and Pn naught is equal to Ni square over Nd, minority carriers from the mass section law. So under low level injection conditions, when Va is not equal to 0, the majority carrier concentration remains essentially unchanged. So Pp equal to Na and N equal to N sub V. So this is like saying that adding a few drops of food coloring to a large bucket of water does not noticeably change the amount of water, even though it changes the color, okay? So these boundary conditions are crucial and key for our analysis because they serve as the starting points for calculating how carriers diffuse throughout the quasi-neutral regions. So now we have arrived at what's often called the law of the junction, the fundamental principle that relates carrier concentrations to the applied voltage. The key insight is that the voltage VA applied to a PN junction falls mostly across the depletion region, assuming low-level injection conditions in the quasi-neutral regions. This is because the depletion region has few free carriers and thus high resistance compared against the quasi-neutral regions. In the depletion region, we can draw two quasi-Fermi levels, one for electrons, F sub n, one for holes, F sub p. These represent the effective energy levels that determine carrier concentrations under non-equilibrium conditions. The carrier concentrations can be expressed in terms of these quasi-Fermi levels, P and N. So multiplying these, we get P times N equals blah, 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 blah. You can do that. The difference between the quasi-Fermi level here equals the voltage that you applied. So here you can plug in the VA. So this gives us the important relationship as denoted in the last line. P times N is equal to N sub I squared times exponential to the QVA over KT. So this is the law of the junction, a powerful relationship that tells us how the product of carrier concentration at any point in the depletion region relates to the applied voltage. So think of this law like a mathematical formula for how much a dam's water flow increases when you open the floodgates by a certain amount. Okay. So now let's take a look at the excess carrier concentration at depletion edges. So using the law of the junction that we have just seen and our boundary conditions, we can now determine the excess magnetic carrier concentrations at the edges of the depletion region. For the P side, we know PP is equal to S of A, and S of P is equal to Ni. We can use a law of the junction. So solving for N sub P, we get N sub P is equal to NP naught times the exponential QVA over KT. So this the excess electron concentration denoted as delta N sub P at the depletion edge can be denoted as this. So this is simply to the NP minus NP naught. Okay, so plugging in here, and instead of NP naught, you can write down Ni square over Na by using mass action law. Okay. So similarly, on the N side, N sub N is equal to Nd, and X P sub N is equal to this. So excess hole concentration is delta P sub N over Xn. It can be described in this equation. All right, so notice here the symmetry in these expressions. The excess magnetic carrier concentration at each depletion region edge is proportional to the equilibrium magnetic carrier concentration multiplied by exponential QVA over KT minus 1. Okay, so you can see that there is symmetry. So this exponential dependence on voltage, right, is what gives the diodes their characteristic nonlinear IB characteristic. Okay, why the IB characteristic of the PN junction diode is not linear? Why is that? You may find out the mathematical reason from this equation. A small change in voltage can lead to a large change in the carrier concentration and thus current. All right, so now let me leave this example for your kind of homework. So please do that by yourself. So now let's take a look at the excess carrier distribution. Now that we know the excess carrier concentration at the depletion region edges, we need to determine how these excess carriers distribute throughout the quasi-neutral regions. So we begin with the magnetic carrier diffusion equations here, where S of P, is the diffusion length for holes. So we have the following boundary conditions, 1 and 2. So for simplicity, we will use a new coordinate system where the depletion region edges are at x prime of 0 and x2 prime of 0, extending into an n region, x2 prime extending into the p region. The general solution to the diffusion equation is delta p sub n x prime is blah, blah, blah. Okay. So from the boundary conditions, we can determine A1 is 0 and A2 is Pn naught times exponential QVA over KT minus 1 to satisfy the condition at the depletion edge. So therefore, the excess hole concentration in the n-type quasi-neutral region denoted as delta P sub n as a function of x prime, Pn naught times exponential QVA over KT minus 1 times exponential minus x prime over NP. Okay. So similarly for electrons in the p-type quasi-neutral region, you can derive the excess electron concentration in p-type region as a function of x2 prime. Yeah, you may find out this similarity between those two equations. So these equations describe how excess minority carriers decrease exponentially with distance from the junction with the characteristic length scale given by the diffusion length. Okay, so here LP and LN. So think of this like a crowd dispersing from a stadium after a game. The density of people is highest near the exit and decreases as you move farther away. Okay. Now let's move on to the PN diode current versus voltage characteristic. Um, Now we can determine the current density by examining, um, oops, okay. So now we can determine the current densities by examining how these excess carriers diffuse out. For the P side, case of N denoted as a diffusion current, and X at X2 prime of 0 right here. At X2 prime of 0, the P side depletion region H, this becomes X J sub N at x2 prime 0, which is corresponding to this part, right? Okay. And similarly for the n side, you can do that. So the total current density is the sum of Jn plus Jp at depletion region either side. So substituting our earlier expressions for answer P naught and Pn naught, you can get to this final equation. So this is the ideal, yeah, there we go. This is the ideal diode equation, often written as, yeah, I is equal to I naught exponential times Q sub exponential QVA over KT minus 1. All right, and this I naught indicates the saturation current density. So the relationship between current and voltage is highly nonlinear due to the exponential term. This is why diodes act as one-way conductors. A small positive voltage leads to a large current, while the negative voltage results in a tiny reverse current. Okay. All right. So some details on the diode saturation current. Yeah, please read all sentences and summary notes. All right. So that's all for today's lecture, and see you in next class. Thank you. Bye bye.